So today I'm going to be talking about preparing topological states using finite-depth circuits and measurements. And first of all, I'd like to mention my collaborators. This work was done with my advisor while I was a grad student at Harvard, Ashvin Vishwanath, and then two postdocs, Thorngren and Ruben Verresen. And there's a series of works which we have put out. And today I'm also going to just quickly flash some very recent collaboration with experiments on realizing topological states with the measurement and feed-forward, which is a collaboration with Continua. So let me just get started. I'd like to start by talking about complexity of quantum states, and in particular the dichotomy of something called short-range entanglement versus long-range entanglement. So short-range entanglement, we would define it as a state where you can reach it from a product state by applying a finite-depth circuit. That is, the depth of the circuit does not scale with the system size. And there are many interesting states with these properties, for example, cluster states or symmetry-protected topological states. And in quantum information, there are many useful things, for example, for measurement-based quantum computation, for example. On the other hand, we have these linear depth circuits, which are sort of harder to prepare, but these states are exactly those states where we want to, for example, perform topological quantum computation or encode form some error correcting code, for example, the toric code. It's known or it can be shown rigorously that to prepare the toric code, the larger the system size you need, the deeper the circuit has to be. And so we're interested in finding if there are ways to prepare these topological orders from both a quantum information perspective and also from a condensed matter perspective. This realizes a non-trivial or interesting phase of matter. Now, very recently, there were two experiments 2 years ago which realized this so-called Z2 toric code or Z2 spin liquid in experiments. One was an experiment by Harvard where they took some Rydberg atom arrays and put them such that the ground state realizes this Z2 spin liquid. And on the other hand, the Google team realized by preparing the toric code using a unitary circuit and measured the stabilizers, and they found very high value for the expectation values of the stabilizers. But as I said, these preparations are a linear depth because it realizes a non-trivial or interesting topological phase. And so if you go to a larger system in the future, it's going to take longer and longer to prepare your interesting state. So it seems that all preparations are slow and not scalable. However, there's a sort of cheat we can use, and actually that's a thing that QI people think about all the time, is to use measurements. It turns out that you can prepare a long-range entangled state by measuring a short-range entangled state. And in terms of thinking in terms of the toric code, what you do, you can think of naively just measuring all the stabilizers, and that's starting from a short-range entangled state and preparing a long-range entangled state. Let me just explain how this works by going through an equivalent procedure. You start with a short-range entangled states. Let me start with the vertices and edges of this square lattice, and I've colored them red and blue. Everything is a product state, and these are the stabilizers. I apply some control Z gates to every vertex edge pair, and this realizes the 2D cluster state on this so-called lattice. And now if I just go ahead and measure all the vertices, depending on the measurement outcome, I'm going to get exactly the toric code term, but some of the stabilizers might be violated. And in that sense, I'm in an excited state of the toric code. But since you know all the measurement outcomes, where this is -1, you can easily, as you would do in error correction, apply a string of operators to pair them up. And after you've done that, all the stabilizers are happy, you realize the toric code ground state. So with a finite depth circuit, one round of measurement and one round of sort of correction from your measurement outcomes, you can deterministically prepare this toric code ground state in a finite depth circuit. And because this measurement is a non-unitary process, a very violent process, we are able to overcome the bound where you require linear depth circuits. This raises the natural question, what else can we prepare? Of course, naturally, all stabilizer states can be prepared this way. You just measure all the stabilizers. But is there anything more? And in this work, I'm going to be talking about how you can go beyond stabilizer codes to actually prepare more interesting states For example, generalizing these toric codes to finite groups are these quantum double models proposed by QIP2023. And we will show that a large class of these can actually be prepared by finite depth circuits and measurements. And a key ingredient in realizing how to do this is what I'm going to show is the deep relation between measuring the cluster state and what is so-called gauging a symmetry. And once we know how to gauge a symmetry, this gives a way to realize gauge theories which exactly realize these quantum double models. And it gives interesting non-abelian stabilizer codes. And at the end of the day, what I have to offer for you is like a cookbook where if you give me your favorite non-abelian state, I can give you a sequence of steps where you initialize, apply some simple gates, measure, and fix depending on that outcome to prepare your non-abelian state. So this is the outline of the talk. I'm going to talk about how to relate the cluster state measurement to something called gauging or Kramers-Wanye duality. I'm going to sidetrack for a bit and talk about realizing this in an experimental platform. And then I'm going to talk about how to prepare these more non-trivial non-abelian states where your group is non-abelian. And I'll even talk about some protocol for preparing one of the easiest non-abelian states. So let's get started with that. Let me talk about, so the cluster state in 1D, there's a deep connection between the cluster state in 1D with the so-called Kramers-Wanye duality. And this comes in many names. Some people call this the gauging map. One thing to note is that if you start with the cluster state with these stabilizers, Z, X, Z, on some bipartite graph like this, if you just simply, if you think of this as a tensor network, you can flip all the blue legs up. And what you have now is an operator. And in particular, this matrix product operator sends an X operator to ZZ. So now you notice that if you just start with the plus state, contract with the plus state everywhere here, this is going to realize a code which has stabilizer ZZ, and that's basically the GHZ state. Similarly, if you start with a 2D cluster state, as I've shown above, and you flip these legs up, it's going to realize an operator that prepares you the toric code state. And in general, actually, any CSS code can be obtained similarly by such an operator by taking the tanagraph, the associated tanagraph to your CSS code. Now, how do we relate, now that we know how to relate cluster state to the Kramers-Wanye duality, how do we realize this duality? Well, that is where measurement comes in. What I'm going to show you is that the known protocol for preparing toric code or GHZ, as I explained, can be recast into this form. So what we did was we start with the product state plus everywhere. We applied a cluster state unitary, which is control Z, and we measured the red sites. I'm going to let this red site input state be an arbitrary wave function. And the claim is that this is exactly what the Kramers-Wanye duality is doing. How do we see that? Well, let's take an X operator here and push it through the unitary, which is control Z. It's a control Z for each pair, so you're going to get Z's at the sides. And now you notice that this X operator, when you absorb it by this plus, it's going to go away. So I've turned X into ZZ. And that is basically this unitary map that maps X to ZZ. And because this picture is symmetric, you can convince yourself X, when you push it down, also becomes ZZ down here. So the discussion here, I put this as a projector, but as I explained previously, it's not hard to fix if you turn this into a measurement. When you have a measurement, there's a possibility that you get either a plus or minus, but even if you get a minus, it's not hard to fix by applying some term to sort of pair up your measurement outcomes. Like in the toric code, you have two E anyons, and you can pair them up. So now what we've done here is we can generalize this and note that this is very similar to what people do in quantum teleportation or measurement-based quantum computation. You start with an arbitrary wave function, and instead of trying to do some gate or performed identity like teleportation, the output state here, you apply to a cluster state, perform some measurement, the output state is sort of the gauge version of your input state, or the result is applied by a Kramers-Wanye map. So the fact that measuring 1D cluster state is GHZ generalizes to the fact that if I perform the 1D Kramers-Wanier map on an arbitrary state in the paramagnetic phase, I would realize a state in the ferromagnetic phase, of which GHZ is a special case. Similarly, if I measure something, a 2D cluster state, and I get the Tor code, that generalizes to the fact that if I apply the 2D Kramers-Wanier on a paramagnetic phase, I'm going to get a gauge, Z2 gauge theory in the D-confined phase, of which Tor code is a special case. So let me just mention some works on how important this correction or feed forward is. And this is some work that we just posted this week in collaboration with Continuum. And you can perform the measurement of stabilizers for the toric code. And what we find here is a measurement-based preparation to prepare the toric code. And by measuring the fidelities, we find, by measuring the expectation value of the stabilizers, we find them all in the 90% range. Moreover, you can even prepare such a toric code state with defects. And so with such a defect, you can sort of create two excitations and braid them. And here you've created some a bound state of the E and M anions, which is created out of this defect because of its non-abelian nature. So let me move on to how do we prepare non-abelian states given this insight. So it turns out that cluster states can be generalized to abelian groups easily. There are abelian groups of these cluster states. There are even non-abelian versions where you can input an arbitrary finite group. Now the issue with generalizing this is, although you can perform projectors on your this generalized cluster state to get the quantum double model, which realizes the non-abelian version, what happens is there's a problem in resolving this into a measurement. Namely, in the abelian case, all my measurement outcomes are so-called abelian anions because they correspond to abelian group. And they're easy to pair up. You notice that in the toric code, you can just apply a bunch of operators to pair up these measurement outcomes that were bad. However, in the non-abelian case, things are worse because you need to apply, it turns out you need to apply a linear depth circuit if you have two such outcomes. And so one way to get around this is instead of performing, trying to gauge a non-abelian symmetry all at once, in words, what we do is we break it down into easier problems where we sequentially gauge abelian symmetries. And at each point, we always pair up abelian things which are easy to pair up. And that's how we get around this problem. So one example, the simplest example of a non-abelian group is this group S3, and you can think of it as the symmetries of a triangle, where you have a Z3 group, which is rotations of this triangle, and a reflection with the Z2. In particular, it's non-abelian because the Z2 action here will flip and make this thing rotate backwards, and that's how it's non-abelian. So the way to prepare the quantum double for this group S3 is that you can start with the layer of a qubit and a qubit. Now note that if I perform this Kramers-Wanier duality or gauging for Z3 and Z2 together, this will just give me a group Z6. That is an abelian group. However, what you can do is if you insert this unitary in the middle, where this unitary is sort of like a controlled operator from Z2 to Z3, this control operator, what it does, it performs something like a charge conjugation. And what it does is it makes sure that the Z2 part is acting in the correct way on the Z3 part. Now, if you insert this right in the middle, one can show rigorously that this map is exactly what gauges an S3 symmetry. And this gives you a way to realize this S3 quantum double model. And by doing that with measurements, we can break it into two rounds. You first gauge this Z3 group. That means measuring the bottom layer where the anions are, and you use feed forward to correct it. And you can do that in 2 rounds. So you can prepare the S3 quantum double using 2 rounds of measurements. It turns out this generalizes naturally to groups that are so-called solvable. And I won't go into the details, but basically if you have a solvable group, you can realize that by a sequence of abelian group extensions. And there's a way to sort of build that up by gauging and apply unitaries such that you get your desired non-abelian group. So at this point, you might say like, oh, measurement is so powerful. I can probably gauge anything in the universe now. Let me tell you that, let me now present some no-goes to that. And surprisingly, it's related to something in algebra, which Galois study. And you might have heard of the fact that the quintic polynomial doesn't have a solution in terms of radicals. Now, what Galois is telling us is actually that basketball is easy, volleyball is easy, but soccer is hard. So, jokes aside, what that means is the symmetry group of this basketball and volleyball is simple enough to be obtained by group extensions, but the symmetry group of the soccer ball is too hard. In particular, we conjecture that quantum doubles for this symmetric group S5, which is the symmetry group of the soccer ball, is too hard to be prepared with finite depth circuits and measurements. So even though you have the power of measurements to help you, we still believe you cannot prepare them using finite depth circuits. I have a few minutes left, so let me try to ask a last question, which is, let's ask if measurement is a scarce resource. So for example, I've said that with a finite number of measurements, you can prepare a lot of these states. But what if I say, I want to minimize the number of rounded measurements? And you might ask, why should we care? Well, multiple rounded measurements requires this feed-forward technology, which is still in development in many platforms. And second, it gives a nice theoretical question to ask, how many rounds does it take to prepare a non-trivial state? In particular, let's ask the extreme question, what if I'm only given one shot, or what one round of measurement? What if you only get one shot? Can you prepare anything that's more interesting, that's not a stabilizer state? And the answer turns out to be yes. You can prepare a non-abelian state, which corresponds to the group D4, the symmetries of this square. And the way it works is that usually, the way I would prepare it, as I explained previously, is you would first measure 2 copies of Tor code, pair stuff up, and then gauge the so-called swap symmetry. We found a way to instead, the problem with the previous round that requires 2 rounds of measurement is that if you have any anyons or any defects left over, once you gauge the swap symmetry, they're going to be, since they transform in the symmetry, they're going to become a doublet after you gauge. And then you're going to get some non-abelian anion, which is a non-trivial representation of the group. A way to get around it is with 2 copies of Tor code, you can convince yourself that you can instead measure the bound state, E1, E2, and M1 and 2. And the difference is that these 2 anions are a singlet. They do not transform under the symmetry. So once you gauge the swap symmetry, they still remain abelian anions. And so turns out you can measure all these anions once, and the result will be this D4 non-abelian state. We even found a way to embed this into a square lattice connectivity for example, these Google chips, and it turns out it will take a depth 11 circuit and a single round of measurement and fixing, independent of the system size. So even though they get larger chips in the future, it will always be this step. So to conclude, I presented a hierarchy of topological orders where one can sort of try to define an equivalence class where 2 states are in the same phase if you can connect them to each other using finite rounds of circuits of measurement. And what we find is that, of course, Tor code can be prepared with 1 round of measurement, but surprisingly, certain non-abelian states can also be performed with 1 round of measurement. Others would require 2 or 3 rounds, but we have some suspicion that there are states that are too hard to be prepared, and these are non-abelian states, for example, S5, and even these funny ones such as Fibonacci anions. So I guess my time is up, but let me just leave some outlook and I'll take questions. Thank you.
Thanks very much. We have time for questions.
Thanks. Why is soccer hard?
Why so sorry?
Soccer.
Oh, because the group.
What I mean is, why does the non-abelian extension of has that anything to do with gauging?
Oh, because I can only gauge abelian groups, and that comes from the fact that you can only pair up abelian anions efficiently. So if you can break that group into a extensions of abelian anyons, then you can prepare that. It turns out S5 for S5 is impossible.
Yes.
And that's the same as you cannot break the polynomials in terms of radicals.
How does this go together with Tyler's work? Can you confirm that subsystem codes could, for abelian phases that Tyler talked about, can be done?
Well, I would say subsystem codes do not represent a phase of matter, so that's sort of outside of the scope of here. Here it's just basically stabilizer codes or generalizations of that.
Do you think you can comment on if it's possible to generalize?
To subsystem codes, I have not thought of that.
Okay.
So further questions on here?
So you can't prepare quantum doubles of like S5 or more with like finite rounds of circuits and measurements. Would it be possible that like, if you like had access to like some more, I don't know, general operations, maybe they're not physically feasible, but then with like finite rounds of them, could you then achieve like higher group orders? Although maybe this is an ill-posed question.
Well, I guess it depends on what ingredients you allowed, but yeah, I guess that's for further exploration. Yes.
Sure.
So you came up with this D4 topological order that was, how did you say this? A single round of?
With some finite depth circuit, a single round of measurement, and like the Tor code, you correct the measurement outcomes in a finite depth.
So were you able to find any other groups like this or characterize what groups?
Yes. So it turns that for groups, it turns out to be something called a nilpotent group of class 2. And one way to think of it is it's the central extension of two abelian groups. And all of these can be prepared.
Thanks for the very nice talk. I have a small question on this, like correcting the measurement outcomes. So, I mean, you're not interested in some like preserving some logical state encoded in the ground state. Because if you were, you would need kind of an extensive classical algorithm that corrects the measurement outcomes. Did you come up with also like a constant depth classical part to correct for the, like to pair up the anyons in essence?
I think it would still be extensive in the classical. Basically, somehow this measurement is pushing the complexity of the quantum part to the classical part.
Sure, that was meant. Thanks.
Further questions?
So if you normally gauge, so there's lots of subtleties with boundary conditions. So what about the twisted boundary conditions and so in your?
So in particular, this thing, if you did it on a system with a boundary, will give you a particular gap boundary. If I remember correctly, it's either where all the charges are fluxes condenses. I need to double check, but you can also get. We think you can also get other boundaries because they're related to 1D phases, which you can also prepare similarly using measurements. So I think you can also get other boundaries by modifying this protocol. But yeah, we haven't wrote it out explicitly, but I think it's possible.
Thanks for the nice talk. So can you extend your method to more generalized quantum double models, like including weak Hopper algebras?
Oh, so so we have a conjecture that this solvability, there's a notion of solvability which generalizes to fusion categories. And so we have a conjecture that any solvable fusion, a modular tensor category, can be similar prepared. But
I see. That's why you conjecture Fibonacci is hard.
Yes, and in that sense, Fibonacci is non-solvable.
I see. Thank you.
If not, then let's thank them again for